Interesting field types. What do we want to take a look at today? If you take a look at our documentation for the 7-something release, you will find a page about all the existing field types. And if you scroll through them, you will see more common types like the existing numbers. There are different ones like some sort of relational data types that help you in certain use cases, ranges, structures, things for aggregating data. And if you scroll through them, you see like, I think it's about a little bit more than 30. So we have a fair share of those different field types. And I want to take a look at a few of those today. Let's make this a little bit bigger so it's easier to see. And the first one I want to take a look at is the new unsigned long field type. You can see here, there is an unsigned long field type. And that one is pretty much what it says. In Java, the maximum value for long is this one because it's signed. So 1 bit is used for the prefix. And with the unsigned long data type, you can store numbers that are bigger than this one. Like this, you can see there's an 8 at the end. And this one gets stored. This one gets searched. And you can also execute range queries on this. And the basic idea here is, apart from being able to probably model your bank account, the most common use case here is probably for networking equipment, which has nowadays bigger counters because of more traffic going on those more than gigabit interfaces probably. So this is a really common use case so that those counters don't overflow that fast as with the 1 bit less that they actually have. And they never tend to go negative. They overflow, they start at 0 again, then they count up again. The next part I want to take a look at is, oh yeah, you can also run aggregations, of course. One thing to be aware of is that you probably will hit the scientific notation pretty often. Just make sure that your parsing library parses as expected. It's not a big deal. Every JSON library should be able to do that. It's just something to have in mind. The next part I want to talk about is the new version field type. And you may know the so-called semantic versioning. It's kind of a rule set. On the one hand, how you should structure your version releases, the major, minor, patch version, what fits into which kind of release. But the other interesting part here usually is that it's more than just the version numbers. You can embed more information. You can see here I created a new index. I should probably delete the old one first and create a new one with a version type. And then we're going to index a few documents. And you can see here I have an alpha version of this release, and I have 5 different versions of a 1.25 release. And the idea is you don't want to have this sorted by the good old ASCII sort. You really want to make sure that this release is the one that is the most current one because it's the only GA release, basically. And if we run this, we could run this without a filter pass, but then would need to scroll to figure out the sorting. So we can add this filter pass. Now we only see the version field, and we see when we sort by my version that the 1.5 version is the first one, the GA version, and then we have the alphas, the betas, the alpha 2 beta version in here, so that the sorting for semantic versioning is basically correct. That probably makes sense if you have an inventory system of your IT inventory, which is also based on this versioning scheme, and you want to make sure that you can sort by this to maybe find old versions of certain software releases. The next one has been added quite some time ago, the so-called flattened data type, but I think it's really interesting and helps a lot for certain use cases. So it's always worth spending some time on it. So let's create an index with a flattened data type. And let's do something that we usually tell people is not a good idea, that we basically have a field that contains arbitrary key value pairs. Imagine that the next document would not contain size, color, and type, but width, height, and length. And so the user is basically able to choose the key names. Indexing this, and we take another look at the mapping. We see that there have not been automatically created new fields of this because everything here again falls under the flattened data type. So one thing that this already prevents is the so-called mapping explosion, that you end up with a lot of fields with different mapping. And also it means that it's not stored sparsely in the inverted index. So when we add a second document, which only contains the last updated field, this works as well. And now the interesting part is we can basically execute a query on the labels field without specifying a subfield. So we didn't have to specify the color here. We're basically searching across all the values of all the fields. You could also embed this field or like nest this field even further if you wanted. But you can also refine your search and just search within a certain subfield, like labels color, just to make sure that this works. If I search for XL in the labels color, this would not work, and we would not get back any data. Of course, this also comes at a price. Like, we haven't added this feature for free, because one of the implementation details is that everything here is stored as a keyword. So this means that you can't do number-based comparisons. So in this example, the timestamp of 2 is basically bigger than this longish Unix-based timestamp that if you did a number-based comparison, it would, of course, be a very different thing. So this is one of the limitations to keep in mind. Everything within a flattened field is treated as a string. But if you just want to be able to offer the user to store arbitrary key values and still be able to search in those, then the flattened field is a really good alternative. This is, for example, used by a fair share of beats in our implementation. The next new feature is the aggregate metric double type. You can see like it's already a rather long name here. And this one allows you to store pre-aggregated data, which you later use for aggregations within a document. So in this example, I basically store like a sales per day index where I have a January document, which just contains information, probably how many orders have been done per day. The minimum number of hours was 13, the maximum was 34, the sum of your sales, and the number of total orders in this example. So if you put that in there, again, the documents get saved. Same for February. And now when we execute a search or an aggregation, we can basically refer to the ag metric field in both cases. And by running this aggregation, we can see that we search for the minimum value, the metric min, across all of the documents. You can see the 5 over here. We search for the maximum value, which was the 35 over here. We are counting the number of documents, and because the number of documents was specified within this single document, it's basically the sum of the value count. And we can also calculate the average by just taking the sum of both sum fields and dividing it through the sum of the value count fields. So you can do some of these aggregations, but of course you're storing way less data, requiring way less space. And if you're not interested in single document granularity, but you kind of want to have some sort of roll-up feature, then this might be an interesting alternative. The last thing I want to demo is the so-called vector feature. So what this basically allows you to do is to describe features of your documents. And when you execute a query, you can kind of use those features as part of a query vector. And this way you could do something like recommendation or preferences and let that one flow into your search as well. So in this example, I create a dense vector field with 3 dimensions. So every document requires an array of 3 floats. And I'm indexing a couple of books here with 3 features. The first one is the number of pages divided by 100. So maybe a reader is interested in shorter or longer books. The second dimension is the rating. And the third dimension is the price, which is kind of an inverted function here, but you could also just flip it around. As you can see here, this garbage collection handbook costs 97 euro. So this number is really small, where Cryptonomicon, I think, is about 7 euro as a book. So if we now index this data, we could execute a search with the preference of the user, and that would be the query vector. In this example, the user prefers short books with a good rating that are rather cheap. So when we run this query, we can see that the first book is indeed rather short, has a good rating, and is also rather cheap with a bit more of 10 bucks, right? This one is also rather short, and if we scroll down to the bottom, we see that a long book like Cryptonomicon, which has more than 1,000 pages actually, is quite at the bottom of the list. And of course, the garbage collection handbook, which I think is 97 bucks, is also at the end of this list. So If we change the query vector and we are interested in long books with a good rating at kind of any price, so it's the middle of the range, we see that Cryptonomicon as a really, really long book is suddenly scored the highest book. The next one would be Data-Intensive Applications, which is also rather long. It has a really good recommendation. And as we're not price sensitive, something like the Garbage Collection Handbook, which also has a really good rating, is high up in the list. So this is a super interesting feature, and you could really use it to kind of customize your search even further. But it also means you have to think about your feature strategy a lot before getting into this place.